Okay. Um, this is Carla McAuliffe. I am the Executive Director of the National Earth Science Teachers Association, and this webinar is brought to you by a collaboration between the American Geosciences Institute, the National Association of Geoscience Teachers, and the National Earth Science Teachers Association. John, if you actually go back a slide, I just want to remind folks who may or may not be familiar with Zoom, we'd like you to make sure that you are muted and you are not showing your camera. The two ways of interaction are via the chat box, which many of you are already using. And there's also a participants box where you can raise your hand or answer yes, no, if Rebecca asks a question like that. Next slide. And so today, this webinar is integrating Earth and Space Science concepts into high school physics and physical science courses. We're very excited to have Rebecca as our organizer. As our presenter. Organizers of this webinar include Aida Awad, who represents NAGT. She's their past president. Ed Roebuck from the American Geosciences Institute. Myself and John McDarris from CERC, who is our technical support. I will introduce Rebecca in just a moment, but I wanted to let you know the flow of the webinar is that we will, after Rebecca's presentation, we will have a discussion and an opportunity for questions and answers, and we'll share some future events. Next slide. Okay, I guess we're sharing future events now. I thought that was at the end. That's fine. Our next webinar is on Thursday, April 12th, and it is featuring two different projects, High Adventure Science from the Concord Consortium, and exploring tectonics through GPS data from UNAVCO, and you can register at that link. After the webinar, this PowerPoint as well as the recording will be posted on the page that you went to register. And you can look at all of our other archived webinars at this URL. Next, okay. All right, so Rebecca is a former high school physics, physical science, and engineering teacher. She was an Einstein Fellow, and she is currently the K-12 program manager at the American Association of Physics Teachers. Rebecca has done an incredible amount of work. She has authored a lot of products, including the NASA Educator Resource Guide for Living in the Age of Airplanes. She's brought in a lot of grant funding. She's a phenomenal teacher and teacher educator. And with that, I will hand it off to you.
All right, thank you so much. I'll go ahead and pop up my screen real quick and make sure you can all see my slides. So thank you so much to all the folks who put this together. It's quite a feat to get so many different things organized, and especially because we're working cross-disciplinarily here. So I'm really happy to see, the earth and space science and the physics come together because so many of us teach so many different types of courses. I know one of the statistics we throw around a lot is that something like 60–70% of high school physics teachers do not just teach physics. And I know the same is probably true of a lot of the earth and space science teachers as well. So basically, I guess I'll say just a little bit about the AAPT first of all, and then some of the goals of this webinar. So the AAPT supports K through higher ed physics and the teaching of physics. So when I say physics teacher, a lot of people think about high school and higher ed university faculty, but the reality is that almost every science teacher at some point is going to have to teach some component of physics, even down at the kindergarten and preschool levels, of course, or at least we hope so. So I'm taking a look in this webinar at some of the cross connections between the content and specifically interdisciplinary learning, which is a little bit different from when we think about the NGSS, we think about those 3 dimensions. Interdisciplinarity it's not a word that's typically used when we talk about the NGSS. We talk about things like cross-cutting concepts, etc. But I really kind of want to dig deeper into the content, the topics. So my goal for this webinar is to help us identify some of those connections, give some very specific examples of how you might consider interdisciplinary learning and teaching. And then I also want to share with you a number of resources that are available for you to consider looking at, but also modeling some of your own ideas after. And as we do think about cross-curricular, interdisciplinary kinds of things, I will say words like the NGSS, the Next Generation Science Standards. But to be fair, I think sometimes it's better to talk about the framework for K through 12 science education, which is that document off of which the standards were based. And that document is much broader, much more high level, and is really a lot more applicable to most states. Even those that have not adopted the NGSS, many of them have modeled their standards off of the framework. So I'm going to try to talk about that more than anything else. And as I already mentioned, many of you are probably familiar with the cross-cutting concepts, things like energy and cycling of matter and energy. I think there's 5 or 6 different cross-cutting concepts within the NGSS. They don't quite touch on interdisciplinarity in the same way as what I'm going to try to talk about today. So I think with that, I'm going to go ahead and start. I just will say, especially for those who are moderating, if I happen to not see a question that pops up in the chat, please just interrupt me at an appropriate time. I'm more than happy to take those questions as we progress so that I don't lose people along the way. So for all of you, feel free to type in the chat if you would like to. All right.
I'm just going to interrupt you for a second. It would be helpful if you put up your hand, if you have a question, because the chat is filling up with lots and lots of stuff.
Great, thank you. So I'm going to go ahead and start, and I know we're a little bit too big probably to really be incredibly interactive at this point, but I just wanted to pull out some of the big ideas, the big core disciplinary core ideas, the DCIs from the framework for K through 12 science education. These are not all of them. But if you just look on the left, we've got some Earth and space science. Again, I think these actually are all 3 of them. On the physics side, I did not include the ones that were explicitly life science or chemistry. I love life science and chemistry, but I wanted to draw your attention to these 2 particular areas. And so on the space science side, Earth's place in the universe, so our solar system, but also things like the sun. How did the universe, or how did the solar system form? How do stars form? What do they do over the period of their life cycles? And why do things move in space? Those are the big ideas in Earth science topic 1, basically. And then also Earth system, so much more terrestrial, focusing a lot more on cycles, forces that shape the Earth, etc. And then the 3rd one really focuses on the Earth and humans' impact upon it, and vice versa. So keep those things in mind as we progress through a number of different examples, and let's see if we can kind of pull some of those things out as we look at different types of interdisciplinary activities. On the physics side, we often break up the DCIs by forces and interactions, which includes Newton's laws, gravitational force, in particular an electromagnetic force. But there's a lot more in there. So when I say Newton's laws, those of us who are familiar with physics realize you cannot teach about forces until, you probably can't teach about forces that well until you've got some good concept of motion and the difference between constant velocity and acceleration. So there's a lot that's packed into all of these big ideas across the Earth and space science and the physics. Energy is another huge one. Fields kind of got shoved into there, which is a little non-traditional for many physics people who used to teach fields probably before they taught circuits. And then the 4th one is waves and electromagnetic radiation. And again, tucked within that, you're going to find things like geometric optics, sound, Not all necessarily at the high school level. Some of it's at the middle school level, and you don't see it at the high school level, and vice versa. So depending upon what grade levels you teach, you might have more or less familiarity with kind of the different dimensions of these big disciplinary ideas. And so I guess, I'd just like you to pause personally and just think about, what connections do you see? Because the NGSS, the framework, although we see energy, those are two words that we see across both of these columns. The reality is that you kind of have to draw a lot of lines on your own. And so I'd like to help with that if possible. And if you have ideas and things that I miss, please feel free to include them in the chat, because I was a high school physics teacher. And the reality is that's my bias here, right? So I'm sure that there are some earth and space science folk in particular who can probably see connections that I'm not seeing myself. So I just want to give an example of what I really mean by integration. And I'm going to start with the first disciplinary core idea that's really physicsy in the NGSS, and that is teaching about forces and interactions, which really means, again, most teachers will start actually about teaching about motion before they can get to forces. One of the very typical things that a high school physics teacher might do is to teach about speed. How do we know if a car is moving fast or if it's moving slow? And so we might get out little cars, for example, that move at constant velocity, little battery-powered cars, and they kind of go across the table, and the students might collect data about where the car was after how many seconds, and then after more seconds, where was the car? They might put that on a graph and make some meaning out of it, and find out how fast did the car go every second, and compare that to other cars. So that's fine. When we start getting into things like acceleration, physicists will have a lot of balls rolling down inclined planes, and I guess what I would like to do is to think about, how can we challenge those same concepts in different contexts, and maybe add some additional content as well. And so on the right, I've got a picture of something that I think can be used, that I know can be used, to teach earth and space science integrated physics. And I'm going to actually give people just a moment to type in the chat and see if you can tell me, what is that a picture of? Let me give people about a 5-second wait time here. See if we can get some fast typers. There we go. CMEs. Okay, it's called a coronal mass ejection. There are solar flares happening, but what you're actually seeing in terms of these big loops, those are coronal mass ejections, which means we're actually getting particles and plasma that's actually getting ejected from the sun. If they end up coming towards us, they take about 1 to 3 days, they can do some damage to our electrical grid. So naturally, students start, when they see pictures like this, they're a little surprised, because when they think about the sun, they think about something that's static, something that's not changing. Those of you who have a deeper familiarity with space science know the sun is extremely active, the sun rotates, the sun has cycles, things that in a physics class we probably wouldn't traditionally talk about. So I want to give you an example of how you can actually incorporate this. I have a link here. You can feel free to copy that. And again, these slides will be available to you, so you don't have to scramble. I'm currently working with a NASA Space Science Education Consortium, where we're actually developing resources to teach specifically about, to teach physics through heliophysics. So we'll have more stuff coming out at that link as well over the next few months. So using something like coronal mass ejections to teach about speed or even acceleration can be lots of fun. And so there's a number of different potential connections to star life cycle elements and just the sun in particular. So I've got it pointing to the first sub-bullet point there. Under physics, we can teach about speed, and I'll share with you exactly how we can accomplish that. But first, I want to show you a coronal mass ejection in motion. By the way, if you look at the time at the bottom of this video, you can see that this happens over a period of, I believe these are minutes. They might be hours, actually. I wonder if I can get an earth and space science person to tell me. I'm not sure what the actual time lapse on that is, but this is happening on our sun fairly frequently. There is a probe called the SOHO, the Solar Helio Observatory, which is above the Earth, and it's got this big camera, and it's got this arm that comes and actually blocks out the sun so that we can just see the corona. And that little white circle right there is actually representative of the diameter of the sun. So we're covering up actually a whole bunch of the edge of the sun, and that's why these total eclipses, our total solar eclipses, are really exciting, because it's one of those few times we can see right up against the edge of the sun. So these things are really quite interesting. And now what's fun about this is you can actually take those videos and screenshot them so the students can see how much time has passed by. And I do recall now this is hours and minutes. So the first, before the colon is hours, and after that is minutes. You can actually have students, they have to make some judgment calls, but you can print this sheet out, and you can use a ruler and have students actually plot how this coronal mass ejection moves away from the center of from the sun. And so they have to make some generalized estimates about where do I start measuring, where do I end measuring. But similar to a car moving across the table, coronal mass ejections, typically when they're close to the sun, they actually appear to be fairly constant in speed. Not always, but in many cases. And so you can get students to plot position versus time. Now, NASA is loaded. If you just Google SOHO NASA, it's loaded with web images and also videos where students can click through and see lots of different types of coronal mass ejections. And students can compare their graphs. They can plot the position. From the position data, they can also calculate the velocity data. So it's very much the same kind of thing that you might do in physics, but now the kids start asking these really wonderful questions, like what is a solar flare? You might start getting into conversations about plasma, different states of matter, electromagnetic effects, all different kinds of things. So that's just one example of potential integration. Actually, before I move on, let me just see, does anybody have any questions or thought or contributions? I see Randy Russell has told me that the time is Greenwich time. That's awesome to know. Kids can learn a little more geography there too. All right, but if there are no questions, I'll just move on. What I will say, though, is that if you go to the link that I've included right here, we actually have a full lesson plan that you can download, and then we've got 2 sets of solar flare data, so you can print off sets so that the students can work together but be working on different sets of data. I think it's got something like 12 or 16 different still images, so it's quite a bit of data that students can plot. Okay, let's see, here's a question. Will our ability to see these phenomena change as the distance between the Earth and the Moon changes over time? I certainly don't think so. This actually, the Moon is not, in this case, these coronal mass ejections, what we're seeing in the picture is, we call it an eclipse. It's not a geophysical eclipse. What we have is, that's actually the plate of the camera that's blocking the sun. So this is actually imagery that's being collected year-round, basically always pointing at the sun. Oh, great. And then the white circle in the center of the image represents the disk of the sun, so you can do scaling and you can find out how far away, how big is the coronal mass ejection, and you can find out its speed relative to the size of the sun, which means you can actually have your students predict, if moving at constant velocity, how long will it take for that coronal mass ejection to get to Earth? What's our advance notice? If we were living on Mars, what's our advance notice? You could do some really interesting risk and survival scenarios with that as well. And then also a notice here that although it looks like these coronal mass ejections are actually coming out perpendicular to us, many of them actually come towards us. And if you get a really good image from SOHO, some of the coronal mass ejections a few days later, no, it's not a few days later, because the particles come at us. there's some interesting physics here where the flare, sometimes the particles will come faster than the flare. But in any case, you can actually see the particle showers as the high energy particles hit the camera, and you see all these snowy sparkles, which is really kind of cool. So, all right, I'm going to move on. That was my first example of something that I think is really straightforward and pretty easy for a physics teacher to consider integrating, or a physical science teacher to consider integrating. All right, here. So another concept that I would teach a lot about electric fields. Electric fields are traditionally really difficult for students to understand. Many of us have interacted, especially with younger kids, with magnetic fields. You place a magnet, put a piece of paper on top of it, and then put some iron filings over it, and you get an interesting pattern that looks like this one here. And I don't know if you can see my cursor, but I'm pointing to the upper left image under equipotential lines. When it comes to teaching about electric fields, though, the only experience that kids really have ever had with electric fields is feeling the hair on their arms standing up when they're near static. Maybe they've touched a Van de Graaff generator and their hair has stood up, but they don't really have a good conceptions for understanding electric fields. So traditionally, the way to go about this is often maybe you look at some pictures like what we've got here. You might interact with voltmeters and have students plot electric fields using some conductive paper or a tank of water, but it just doesn't really often come across as really kinesthetic, like the students often need with something that is completely invisible to them, and they often can't sense at all. So I had an idea a number of years ago. The young women on the right were my students. I think it was my second to last year of teaching. And I just felt like I really needed to make my unit on electric fields much more exciting. So I got out some clay. I took inspiration from an earth science teacher. And for this one, if you'd like a copy of the lesson, you'll actually have to drop me an email to get access because it's currently on our members only site. So feel free to drop me an email. I'd be happy to send it to you. But I'm going to go ahead and start off with I think I've got a video here, which I'll show you in just a second. But as I share with you the resource, keep in mind energy and energy flow, shapes of the earth, things that shape the earth, as well as the different, I know many of us teach topography and topographical maps. It doesn't explicitly come out in the NGSS, but it's hard to interpret and understand forces that shape the earth without having a good three-dimensional understanding that the earth is not a flat place, and maybe we need to look at some maps to make sense of the earth's different shifting structures. In physics, when I teach about electric fields, there's a strong connection to electromagnetic forces, also, as you'll see in a moment, gravitational forces, and broadly fields. I'm not sure how many of you have seen this, but this is really where I took inspiration. If any of you happen to be like at the NSTA, you might see one of these. I often see them at conferences. So what we have here is it's a sandbox, and as you move the sand around, you have a projector up above that basically can identify, it can measure the distance, so the depth, and is able to superimpose the altitude lines, the contour lines, and also to put some nice visualization for water flow and things like that. So I'll just let you look at that for another moment, let it play.
Try to recreate the features by manipulating the sand. I can take one mound, make it into two mounds.
So these things are really pretty awesome, but they cost, I think, a lot of money to get, and most schools probably don't have them. I certainly did not have one. Many earth science teachers have these little tanks of water that have a little plastic mountain on them, and you pour colored water progressively, and you see the different contours. But I also didn't have that in my classroom, so I came up with the next best thing, and I said, well, let's take a look at some topographical maps. So here's a very, very straightforward, as an adult learner for me, this is straightforward. For children, not so much, who've seen this for the first time, but it gives you a sense that you can use flat two-dimensional topographical maps to create a kind of 3D visualization. And so the line A to B cuts through that object, and then we see the actual elevation at the bottom. Now, what inspired me is I saw, and I'm not the first person to come up with this, but what I saw were some really interesting connections to electric fields. So if you're not with me still, we'll see if we can get these ideas to connect. I'm going to show you a video that came out a couple of years ago from a really awesome physics teacher in California that deals with electricity and electric fields, and also a little bit of chemistry too, because he uses potassium permanganate crystals dropped onto a saltwater soaked piece of coffee filter. So I'm going to just let this play for a moment. I think you probably can't hear the audio, so just bear with me as you watch the pretty patterns. So I'm going to pause it here for a moment because many of you might recognize that this is the exact same kind of pattern that you see with that bar magnet with the iron filings. Most students never see this with electric fields. And so here what we have are two electrodes, a positive and a negative, with a very, very high voltage across it that's actually causing the particles to, the molecules to move through that paper and produce that pattern. We'll connect this to topographical maps in a moment. I'm going to just show you a few other visualizations from this video. There's lots of different shapes. Great. So keep that in mind, and then think about the images that I showed you at the kind of start of the second example. Here we have a positive and a negative, and these dotted lines are very similar to the contour lines that you would get on a topographical map. So now it's possible that you might be able to start to see something happening here. If this is positive and this is negative, it's kind of similar to having a mountain and a conical valley, basically, or to have two mountains. And you might notice that these field lines, which show us electric force, are somewhat similar to rain lines. If water were to drop on top of a mountain, it would flow away from it, or it would be pulled towards that direction. Similar to the positive and the negative, it would flow from the positive down into the conical valley, or things like that. So I found that my students really, really connected to this. So watching the video is great, but then I'd actually have my students get out a topographical map. I would get one such as this one here, try to make it not too complicated, and I would ask my students to actually build it. So we'd go from looking at a topographical map, with which most of my high school physics students were familiar with. They would build themselves a mountain, and after they built the mountain, we would start talking about what are the parallels with an electric field. Where would the positive source charges be? Where would the negative source charges be? If you placed an electron on the mountain, which way would it go? If you placed a positive particle that could flow freely, which way would it go? And we were able to make some really interesting analogies between gravitational fields and electric fields. And we could imagine a world where in a gravitational field, stuff really only goes down, right? Relatively down to the ground. In an electric field, you have an interesting world in which some particles flow up to the top of a mountain and some particles flow down. And it leads to these really rich, interesting discussions that I'm sure one could do a lot more with than what I did. So let's see here. Eddie Goldstein's asking, is there a way to look at topographical map and figure out the watersheds? Absolutely. So there's another kind of earth science connection. And I don't know, I'm sure all of you are familiar with the crinkling up the paper, drawing with marker on the ridges and dropping water on it, and you can see the watersheds. That's another kind of kinesthetic thing that you could do that I think could have some connection to this as well. But feel free to keep talking about that in the chat. So this is just an example. So for this whole idea, if you send me an email, I'm happy to send you a copy of the lesson plan that goes with this. But what we actually do is after the kids have done this activity, we go back to the video and we look at still images of each different scenario, and I ask them to draw for me the contour lines and explain the three-dimensional nature of that electric field. So as an example, in this case, we have we've got the positive side connected to this point here, which makes kind of like a mountain. And here with this bar, it's like a long ridge. And I'm sure that there is a name for this, and I don't know what the name would be for kind of an inverted ridge. So if anybody knows, please educate me, because the answer is I don't know. And I don't know if anybody has a reference to the crinkling up paper activity, so if somebody could find that for Eddie, I'm sure he would appreciate it. And I'm sure you can find it all on the web too. So that's electric fields for you. Like I said, there's also connections to gravitational fields. And I guess I wanted to just take a pause here at the end of the second idea and just briefly share that not only should we be looking for activities when we look at integration, I think it's also really important to look at assessments. And there's a really, really incredible website, and I'm sorry I didn't paste it on here, it'll be on the other ones, called Physport, PHYSPORT.org, which have nationally normed and highly validated assessments. I happen to pull one that's all about the Newtonian gravity concept inventory, which has a number of questions about astronomical astronomy and gravity, universal gravitation, and it's slightly connected. Something I didn't want you to miss, because I think it's really quite fantastic. All right, before I move on, if anybody has any questions, feel free to post them in the chat. All right. So the third idea I wanted to share has to do with waves and electromagnetic radiation, especially in the middle school NGSS. There's a lot, and also very much in elementary, there's a lot about what happens when you place an object that's opaque, what happens to the light that's trying to go through it, and what happens behind it. So how are shadows formed? How does light travel? And understanding light rays as geometric light rays. And a lot of times we'll do activities, we have the kids get their hands out, get their buddies out, make shadow puppets. But when you teach about shadows and optics, what a wonderful opportunity to start thinking about eclipses. And so the image over here to the right, we actually, if you look in the lower right-hand corner, I was working with a couple of my colleagues here. We went outside and we were modeling total solar and lunar eclipses and taking a look at not only how shadows fell on the Earth because of the moon, but also what kind of a shadow would form on a plane behind the Earth system. That's actually a really, really important concept, because the majority of students believe that when you ask them, when they think about it, students will often assume that every month we have a solar eclipse and every month we have a lunar eclipse, because the images we look at are two-dimensional. Students don't understand that there's a tilt involved and that the moon doesn't always line up with the sun from our perspective. And so understanding how the light how the moon does not always block the light of the sun, I think is really important, and knowing that there is a shadow that would be produced in space. Looks like Carla is sharing some really awesome resources, so that's great. This particular resource that I'm mentioning, the link is right here. It was also developed with NASA and has been used in a number of different environments to teach future teachers as well as to teach undergraduates. Has worked out really quite well, and I think is it's a little different because we ask the students to draw in the shadows, and that's something we often don't ask them to do. at least not that I've seen in physics courses. Here there's potential for connections to things like orbital motion, understanding not just how frequently the moon goes around the Earth, but also understanding that it's not a flat plane with respect to the sun, that it does have a tilt. And then again, focusing on geometric properties and understanding that light travels in straight lines, etc. Again, I mentioned Physport. It is listed here actually on this slide. There's a great assessment called the Lunar Phases Concept Inventory, which you may feel, how is that related to eclipses? The reality is that we've found that students who do not understand lunar phases have an extremely difficult time being able to explain eclipses appropriately. So something that I really think goes hand in hand and everybody could benefit from. And then the last example that I'd like to share, again, has to do with waves and electromagnetic radiation, but it has more to do with the spectrum than geometric properties of light. In traditional physics, we would probably teach Roy G. Biv. We'd teach, from radio waves to gamma rays. We might do some calculations about energy. We might do some color mixing, but far too infrequently do we think about things like stars and black body radiation. So with Earth and Space Science Integrated Physics, I would encourage you to think about a really, really, really fun activity that was written up in the Physics Teacher. Actually, all of these ideas at some point have been written up in the Physics Teacher magazine, which has to do with buttons representing photons. And let's see here. For this one, you'll also have to just drop me an email to get access to the lesson. I'm sorry, they're not all open access. Some of them are stored on our website that's protected to members, but I'm more than happy to share that with you. Let's see here. So again, connections to nuclear fusion, composition of stars, energy. There's a lot of different things you can pull out of this activity. So I want to take a moment to go through it because I think it's really fun. It does take some prep work, and a significant amount of prep work, but it's prep work that you can give to a student who maybe needs to spend some extra time in the classroom because, I don't know, maybe they misbehaved, or if you have like an intern, it's counting buttons, so it's not conceptually a difficult lab to prepare for. So the idea with this lab is you actually blow up a red, a white, and a blue balloon, and you fill them up with an appropriate number of colored buttons. And for this one, we're just simplifying it to red, orange, yellow, green, and blue. And the buttons get put inside the balloons before they're blown up, and they're all blown up to be about the same size. Those balloons represent a red, a white, and a blue star. Students may already know a little bit about red, white, and blue stars, that they have different temperatures and things like that. And what the students will do is they actually pop the balloons, and you can, if you pop them right next to the knot, they don't kaploom, go everywhere. They actually decrease slowly, and you can pour out the buttons. The students make a histogram with the buttons and then draw it in, and they can make some interesting observations, like the red star has buttons that are mostly on the red and orange end of the spectrum. The white star has more in the green, which is a real shocker to kids because kids think that white stars are just white. And they don't know that white stars are actually perceived as green, as in the case of our own star. And then blue stars have mostly blue. But in addition to the breakup or the proportion of the color, they also see and physically feel that the blue star has got way, way, way more photons that are emanating from it. It is a lot more energetic. So they're able to make a number of different claims about the temperature, the luminosity of the star, etc., depending upon how much they know about quantitative, how much they know about astronomy. But now here's where it becomes really, really fun. So after you've done that, I give students 3 baggies that are unknown astronomical objects, and they also have buttons in them. And when you break out their buttons and make the histograms, we find some really wonky graphs. Instead of having these nice smooth curves like you would see in a black body spectrum, you see for like letter A, that it's like all the purple and the green is missing. What's with that? Or if you look at the B, it's like we have a smooth curve, except we've got extra purples and extra reds. And if we look at C, we've only got purples and greens. I don't know what kind of star that makes. So this is an opportunity to teach students about how we do spectroscopy and the fact that when we're looking at a star, well, sometimes we're looking at things that are giving off glowing gas that is not a star, first of all, certain nebula and things. But it's also possible that we're observing a star and the star's light is coming through to us, but some of it's getting absorbed. And so we introduce model atoms that either absorb or give off light at specific colored frequencies. And from their data, they're able to deduce what color star the unknown baggie is composed of, if it's a star, and what is blocking it or what is being added to it. So in the case of object A, we have a, let's see here. Do I have these backwards? I think I may have these backwards, these baggies. And I apologize for that. The answer key does not match on this. It's correct in the document that I have to share, that I'll be sharing. But basically, with object A, you've got some kind of a cool gas that's absorbing the violet and the green, and it corresponds to one of the model atoms. So it's really, really quite fun to do. And in addition to that, you can extend these things with so many different kinds of online resources that have big data sets. And that's something that I think earth and space science and environmental science teachers are often very good at, is collecting that real world data and using those data sets. Physics teachers, and I'll speak for myself here, I think I was a little bit more hesitant to do that. It wasn't kind of part of my culture because I was so focused on these underlying fundamental principles that could be emphasized by a single equation. And so big data seemed less attractive to me. But now I understand how really rich it is and how it can enhance the understanding and application of those fundamental principles. So that's my fourth example. Additional extended connections into assessments. There's a star properties concept inventory. There's a light and spectroscopy concept inventory. Just visit Physport. If you want to get teacher access to those things, it's totally free, but you do have to register as a teacher user and get approved by one of our staff members at AAPT, just so that stuff is not ending up in other people's and students in students' hands. If you have any troubles with that, let me know. And I know I'm getting down to time here, so I just want to share real quickly, if you're interested in more about physics and how it fits in the NGSS and how it refers to Earth and space science and could interact, we do have a free download if you just Google AAPT NGSS, I think it pops up. If you're at NSTA, you can pick up a hard copy for $5. So it's basically the at-cost printing. And in that, we list the connections to the various other sciences. We list many of the Earth and space science standards and lists the essential physics that's in there. And then in terms of following up, there's a lot of follow-up activities. You already heard from Carla. I just wanted to say one additional thing, not associated explicitly with Nesta, I believe, being hosted by I Teach Physics. There will be a Twitter chat about today's webinar on Saturday at 10 a.m. Eastern. I won't be there, unfortunately. I'll be doing a separate webinar, but it's an opportunity to continue the conversation. And then the last thing that I wanted to share is if you happen to be at NSTA on March 17th, David Thasenga and I will both be presenting. We'll actually be doing some hands-on activities. And I hope you can also stop by if you happen to be in Washington, D.C. during the summer for our annual summer meeting for the AAPT. We'll also have a whole bunch of hands-on activities, including many of these. So I know that's kind of a lot. I'm happy to take questions. And Carla, I'll hand it back over to you to close things out.
Are there questions for Rebecca?
Thank you for coming.
I'm not seeing any questions. John, was there a slide to put back up again at the end?
Yep, there you go.
Okay, so we would like to invite you on the same page that we advertised. We'd like to invite you to join in an online discussion about this webinar. We'll keep this open for about a week. And we have some guided questions for you to share with us on the webinar. Well, if there are no additional questions, Rebecca, is there anything you wanted to say?
No, just thank you. And I guess I'd also just say I would be interested in your ideas if anybody has ideas and would like us to develop lessons around. You may have some that are already developed, but we're also actively looking for ideas that we can disseminate, and we'd be, of course, give you your credit, put your name all over it too. So if you're interested in disseminating, I think we'd be very happy to hear those ideas.
So thank you everyone for coming, and please do consider joining the online discussion. And we'll remind you again that the next webinar is after NSTA, Thursday, April 12th. And that's going to be two different groups, the Concord Consortium and UNAVCO, as well as you can look at all of our archived webinars on the link up there. If you happen to be going to NSTA, I would strongly invite you and encourage you to attend our Friends of Earth Science reception on Saturday evening. You can find all of NESTA's events, including Rebecca's talk for NSTA, at our website, which is nestednet.org. Thank you again, everyone.